Assalamu alaikum. I hope all of you are well and doing excellent. So, under these circumstances that we are facing now, we are going to be together throughout this classroom. However, according to your request regarding the video record of carboxylic acid derivative lecture, I'm going to be recording this video in 3 parts to explain the carboxylic acid derivative and make it with a small size to get it easy for download. However, the first part we are going to start with the carboxylic acid derivative introduction. The main thing with the difference between the carboxylic acid derivative and the carboxylic, it should be replace the hydroxyl group with an electronegative atom. This is the one important thing, that we are replacing the hydroxyl group with an electronegative atom. One more thing, this electronegative atom that are replacing should be good leaving a group for substitution reaction. Like for example, we are replacing the hydroxyl group with any halogen X to get acid halide, or replacing the hydroxyl group with OR, which is going to be also electronegative group and good leaving a group, or with amide, thioester. There is different type of carboxylic acid derivative like amide, thioester, ester, acyl thiophosphate. There is many. Anyway, the most important thing in this slide is what I want is just replacing the hydroxyl group with an electronegative atom, and that should be good leaving a group. Okay, let's start with the name of the carboxylic acid. The first type of carboxylic acid name is acid halide. For the acid halide, we are just replacing the IC as an acid compound, IC acid, by YL. For example, like last time, this compound we are just naming as acetic acid if there is hydroxyl group here. We are just naming it as acetic acid. Now we just replacing the IC with YL, then we are just saying acetyl chloride. The second compound is benzoic acid, or benzoic acid if there is hydroxyl group here. We are just replacing the hydroxyl group with the BR, so we are saying benzoyl, YL, benzoyl bromide, and so on. The second type of carboxylic acid derivative is the acid anhydride. For the acid anhydride, there is two different types of acid anhydride. Is either symmetric, which is going to be the left side is equal to the right side or same, or unsymmetric, which is going to be the right side is different from the left side. Anyway, let's start with the first one. For the first one, if we want to name it, is the same as carboxylic acid. We are just putting anhydride in the end, the word of anhydride in the end, like this one. This part is acetic acid, so we are just saying acetic anhydride. This one is benzoic acid, we are just saying benzoic anhydride. We just replace the acid word with anhydride word. For the one is unsymmetric, we are two different parts from acid. This one is coming from benzoic acid, and this one is coming from acetic. So A is before B in the alphabetic arrangement. So we are just saying acetic benzoic anhydride. Let me take another example for this one. Okay. If we are saying we have this compound CH3, CH2, C double bond O, O, C double bond O, and here we have benzene ring. So for this compound, this part is ethanoic, and this part is benzoic. So in this case, we are just naming it as benzoic ethanoic anhydride, because B in the alphabetic arrangement is going to be before E. Anyway, let's return back. This is for anhydride. The third part of the carboxylic acid derivative is the amide. For the amide compound, we just deleted the IC we just delete the IC for the acid compound from the acid compound and replace it by amide word. Like this compound. Last time is acetic acid if there is hydroxyl group. We just saying amide. We delete. Last time is acetic. We just delete the acetic acid and replace it with amide. We just put it amide. It's too easy. This one is for the primary amide. Like the second example is this one is hexaamide. What about the amide secondary or tertiary amide? In this case there is something different. We just differentiate between the first primary or secondary and tertiary by N. We just put N and then we mention for the substitution on the N. The substitution is going to be different from the substitution of carbonyl. The substitution of carbonyl, this one is for amide word, but the one substitution on the N is different, is going to be mentioned by N, differentiate by N. I'm just saying N-methyl propanamide. For this compound, there is two substitution on the N, so we are saying NN, that means it's tertiary. NN dimethyl cyclo. So it's different. By this thing, we can differentiate between the primary, secondary, and tertiary from the name. For the tertiary, we are saying NN, double N. For the secondary, we are saying N. For the one primary, there is no any substitution on nitrogen, just hydrogen, 2 hydrogen, NH2. That means we are saying just amide. Okay. The fourth part of carboxylic acid derivative is ester. For the ester, we just deleting the IC and replace it by ATE, like this one. One more thing. We should mention first for the alcohol part in the name. We just mention first the alcohol part, then the carboxylic acid part. Like for this compound, the alcohol part is ethyl, so we just saying ethyl, and then the carboxylic acid part acetate. For this compound, this one is diester. We just saying dimethyl, the alcohol part first, and this one is either you saying propanoate or malanoate as the commercial name. For the third compound, the alcohol part is tertiary butyl, so we are saying the tertiary butyl cyclohexane carboxylate. While we saying carboxylate, because this is the carbonyl compound. Carboxylate is mentioned for the carbonyl compound. The cyclohexane is cyclohexane, this one, and this is the carbonyl we just mentioned for the carboxylate. Okay. Now we are talking in general about the nucleophilic substitution reaction. Before that, just I want to mention for something important that different from the other. In the carboxylic acid derivative, so this atom, as I mentioned previous, must be a good leaving group first, second, and should be an electronegative atom. This one can be differentiated from the aldehyde or ketone, because in aldehyde and ketone, this part is not more electronegative atom, is almost same electronegative atom with the one on the other side. This is the most important thing. This is what I can differentiate between the carboxylic acid derivative and aldehyde or ketone. If we are saying here in a question, while the carboxylic acid derivative is more reactive than aldehyde or than ketone, then the reason is going to be because this one, this part, one of the part of the carbonyl part is getting more electronegative and more electronegative group atom and good leaving group. The general mechanism for this nucleophilic substitution is just getting the nucleophilic is going to attack the carbonyl compound the carbon of carbonic compound, then the double bond is going to be open forward oxygen, then the oxygen is getting one bond on negative charge. The intermediate is getting all the compound together, the nucleophilic and the leaving group and R. In this case, the negative charge is going to be rearrangement and become forward the carbon to get the carbonyl and nucleophilic, and this is the leaving group is going to be getting out. This is general mechanism for all the compound of derivative carboxylic acid. The reactivity of carboxylic acid. Here just mention for one important thing, that for the reactivity, the steric hindrance is play a main role in the reactivity of carboxylic acid. So for example, the one with the 3 substitution on the alpha carbon of carbonyl group is getting less reactivity because of the steric hindrance, steric effect. This one, let me say, if the R is CH3, so it's getting more bulk. The one is bulk, more bulk is the one is getting less reactivity. The one is bulk is getting less reactivity. The one without bulk is getting high reactivity. Let me take one example for that. Okay. Just let me erase this one. Okay. Compare between these two compounds for the reactivity of carboxylic derivative. Okay, first compound, let me say, we have this one. Here is carbon, CH3 tertiary butyl, CH3, CH3, and here C double bond OX. Compare this compound, the reactivity of this compound with C double bond O, CH benzene ring. X. So now, which compound is more reactive than the other? This one is CH, and here is a quaternary carbon, CH2, sorry. So this one is getting less bulk than this, the tertiary butyl. So this one is higher reactivity than the first one. Why? Because the bulk here beside the carbonyl is less than the bulk here. So the bulk is getting direct effect on the reactivity of the carboxylic acid derivative. The one is less bulk, the one is higher reactivity. This is the first note. The second note, the one is more polar is higher reactivity than the one is less polar, like the amide and acid halide. The amide is less polar. Why less polar? Because this carbonyl group, the double bond is getting resonance between oxygen and amine, and most of the time is spending the electron in the nitrogen beside the nitrogen. Why? Because nitrogen is higher electronegativity than and have one orbital empty orbital, so getting the electron most of the time beside the nitrogen. In this case, so the losing of hydrogen is not getting the easier, but for the carboxylic acid halide is getting the chloride, which is getting higher electronegativity than the others. So in this case, higher electronegativity is higher polar. That's why we are saying the reactivity of carboxylic acid halide is higher than the amide. So the conclusion is two things. The first one is which is controlling the reactivity. The first one is the bulk, steric hindrance. The second one is the polarity of the compound. For the aromatic substitution, electrophilic substitution, same as we are mentioning previous. If we have benzene ring, aromatic ring, plus this one, the acid halide, is getting reactivity higher than this one, is getting reactivity higher than the reaction of amide with aromatic ring, with benzene ring. Why? Because the amide is less reactivity, because the polarity of amide is less than the electronegativity of a chloride, the acid halide. So the acid halide, the chloride, is easy to remove, but the amide group is not easy to remove on compare with the acid chloride. The reaction of carboxylic acid derivative. In general, the general scheme of reactions of carboxylic acid derivative is getting the first one. If we have this compound as a chloride X, is hydrolyzed with water to get the carboxylic acid. Is hydrolyzed with the water is to get the carboxylic acid. For example, if we have this one, just let me clean this one. If we have acid halide, for example, CH3, C double bond O X, this one with water H2O is direct getting hydrolysis to get CH3, getting the partner compound, the carboxylic acid OH. This is called hydrolysis. This one is hydrolysis. The second one is the reaction between the acid halide or the carboxylic acid derivative with Kuhul to get replacement and getting Ester compound. Here the condition is either base or acid as a catalyst, or reaction with the amide to get the amide. The one is different is here, and the one is important is here. The reduction, hydrogenation of acid halide or acid derivative is getting aldehyde, not ketone. Why? Because this one is terminal. The carbonyl group is terminal. I repeat it. The carboxylic acid derivative is getting hydrolyzed to get the aldehyde compound. Why not getting ketone? Because this one is terminal. How can I get ketone? By reaction of the carboxylic acid derivative with RMG, Grignard reaction. Then I will get ketone. You need to differentiate between this one and need to be careful with this reaction. The reaction of acid derivative with RMG, Grignard reaction, is getting ketone. The hydrogenation is getting aldehyde. This is one important thing. Okay, next slide. How can I convert it, the carboxylic acid to the acid halide? How can I convert it, the carboxylic acid to acid halide? We have two different agents that we are usually using to convert it, the carboxylic acid to acid halide. The first one is the thionyl chloride. The second one is oxalyl chloride, which is not famous. Cl, C double bond O, C double bond O, Cl. This is two agent. The first one is thionyl, which is going to be the most famous one. The second one is the thionyl chloride. The reaction and the mechanism of this reaction is just too simple and general. The electron pair of oxygen is going to attack the thiol, the S atom, and then getting intermediate, which is all the compound is together, all the substitution together, and getting one more bond on the oxygen of the hydroxyl group to get positive charge, 3 bond getting positive charge. This one will remove the HCl. This one will remove the HCl to get a stable compound, and then again the HCl, the one is removing the HCl, is going to attack the carbon of carbonyl group, and getting rearrangement to get the acid halide. It's just the main thing in this mechanism is two things. First, the electron pair of carbonyl compound is attack the thiol atom to get an intermediate, this one. This intermediate will remove the HCl, and the removing HCl is going to attack the carbon, this one, the carbon of carbonyl, to get the intermediate, this intermediate, and then rearrangement this intermediate to get the acid halide. This is the general mechanism for the acid halide. Anyway, the preparation of the acetic anhydride. Usually for the acetic anhydride we use two equivalent from acid. We use two equivalent from acid at high temperature to get condensation reaction, and giving to us the anhydride, acetic anhydride compound. For the esterification, we have two type of reaction to prepare the esterification. The first by base catalyst, for example. Let me explain this one clear. If we have R C double bond or carboxylic acid, first we react with sodium hydroxide as acid condition, NaOH, to get salt, carboxylic acid salt, RC double bond ONA. This one is going to react with the plus, let's take a black color, any alcohol, ROH, to get R C double bond O R. This one is this of alcohol, and this part is coming from acid. It's coming from acid. Okay, so this is a Clemmensen reaction. Let me go back. Clemmensen reaction is getting, first we are making the salt, carboxylic acid salt, by reaction of carboxylic acid with sodium hydroxide, and then this sodium hydroxide is either react with halide alkyl to get salt, or with the carboxylic, with the alcohol, either with alcohol and or with the acid halide alkyl. Usually, and the most famous one is the halide alkyl, because it's more faster reaction with good product and yield. That's why usually they mention just for the halide alkyl. Anyway, the reaction is getting by mechanism SN2. While SN2 not SN1, because this is not bulk. So the mechanism is going to be SN2. This one is important. If I bring in the exam, write the mechanism of ester by base condition is going to be SN2, which we are already mentioning and taking previous with the halide alkyl. Anyway, the second method for preparation of ester is Fischer esterification reaction. For the Fischer esterification reaction, usually is getting by acid condition. They are using acid condition. How is the mechanism is going to be? Let me say. This is the mechanism for the Fischer esterification. First, the HCl, the acid condition, is going to protonate the carbonyl, the oxygen of carbonyl compound, to get H, protonated OH. The oxygen is going to be 3 bond, so the positive charge is going to be appear on the oxygen of carbonyl compound, and then the alcohol compound is going to attack the carbon of the carbonyl, to give the intermediate. This is the intermediate. All the compound is getting together. Hydroxyl group, and then the alcohol. Now this hydrogen is getting out. After getting out, this hydrogen is going to protonate this hydroxy. See, it's going to protonate this hydroxy to get water, which is going to be elimination. is getting elimination. How, from where with this water? This is the hydroxide, and this is the hydrogen of alcohol. The hydrogen is going to move for the hydroxide because the OH is going to attack the hydrogen and is getting water. This water is going to eliminate, and after eliminate this water, then we are getting the carbonyl compound. This one is eliminate the water, and then the hydroxide, the second hydroxide, is getting rearrangement to get double bond, C double bond, which is going to attack by water to get again the acid, the catalyst come. This is the general mechanism for the ester. So to here I'm going to stop the first part. I'm going to end the first part, and then wait me for the second part. See you.